Uh, Good morning, everyone. Thank you for joining the distinguished webinar series in artificial intelligence cybersecurity. Our speaker for this week is Dr. Slaven Peles. He's a senior computational scientist at Oak Ridge National Lab. The title for today's talk is Next Generation Power Systems Modeling and Computations. Dr. Slaven is a senior computational scientist at ORNL. His primary research interests are in bridging existing technology gaps in computational science related to challenges in domains such as power systems, microgrids, and energy-efficient buildings. Recently, Dr. Peles led ExaGO, ExaSGD Stochastic Grid Dynamics at Exascale project involving 5 national labs in Stanford University, which introduced Exascale Computing to power system analysis. Before joining ORNL, Dr. Peles was a chief scientist, optimization and controls at PNNL. He has also been adjunct faculty at Institute for Computational and Mathematical Engineering at Stanford University. Previously, Dr. Peles worked at Lawrence Livermore National Laboratory, where he was a member of Institutional Center of Excellence, working on deployment of Sierra supercomputer, as well as member of Sundial's S-Library development team. Before joining National Laboratory System, Dr. Peles was a researcher at United Technologies, now Radiant Technologies Corporation, where he led several aerospace and energy-related research projects. Dr. Peles got his PhD degree in physics from University of Manitoba in Canada and BSc degree also in physics from University of Sarajevo, Bosnia and Herzegovina. Dr. Slaven, thank you so much for spending your time with us this morning, and I appreciate the time and effort for this webinar. We are so honored to have you as part of our webinar series. The floor is yours. Now you can share your screen.
Thank you, Prakash, and thank you for invitation, and thank you all for coming. I hope I will meet the expectations that you raised so high. So let me just try to share my slides. Give me a moment. Okay. Can you see my slides?
Yes.
Yes.
Okay, and I will switch to presenter mode, and I hope that you can still see what I'm sharing.
Yes.
Awesome. Awesome. So thank you all for coming. And I would like a little bit to talk about activities that we do at Oak Ridge National Laboratory. And as my title says, my primary interest is high performance computing and analysis of complex systems. This is extended version of the talk that I gave at PES general meeting next year, and it's of course updated with the new results that we got so far. This work has been done as a part of the Exascale Computing project. This is joint effort of DOE Office of Science and National Nuclear Security Administration, and have included quite a few people from different laboratories. So the work that I will be talking about today includes people who I listed here, and I will mention their names as I go along and give credit where credit is due. So this is certainly not a single person effort. This has been a large interdisciplinary work that involved power systems engineers, mathematicians, computational scientists, and software developers and engineers. So as you may already know, at Oak Ridge, we are hosting world's first exascale computer. We are very proud of that accomplishment, and right now this computer is the world's most powerful computer, and at the same time the greenest computer, because it generates the largest number of computations per watt of power. So quite a few accomplishments in here. But before we move on to what we do on this computer, I would like to dispel some myths about supercomputing. What we have done within the Exascale Computing project, we developed computational methods and numerical methods that can scale up to unprecedented size. We were able to deploy them on the machine that is currently the largest and fastest supercomputer in the world. But this does not mean that if we talk about exascale computing, that exascale computing needs a really big iron to run onto it. What it means that the same code that will run efficiently on your laptop, you will be able to run that same code on the fastest supercomputer that you can think of. So this is what we mean by exascale computing. So this is not something that is only for few privileged who have access to these super large machines. This is something that everyone can use, and it guarantees you that in the future, whenever you get a faster, better machine, you will be able to take advantage of these hardware resources. The other myth is that, why should I care about high performance computing when when in my work all I need is off-the-shelf hardware and I don't need parallel solutions for the work that I do. And this is also a bit misleading because even the cheapest off-the-shelf workstations today, they have 8 to 12 cores in their processor. So there is still some parallelization that takes place in there. And if you are using single thread computing, that means that you are using about 10% of the resources, CPU resources that you have on that machine. And this is more damaging than one would think, because typically L1 cache is assigned to a specific core. So not only that you are using less processing power, you are limited how fast you can bring your data to that processor. And these are all things that one need to consider when before dismissing parallel computing altogether. And unfortunately, there are many areas in engineering where people are just very dismissive and say, okay, we've been doing this for the last 20 years. It worked well for us. Parallel computing is some exotic thing. It is not. So why do we care about heterogeneous computing? Why is this exascale computing so important? Is because of the technology limitations related to semiconductor industry. There is that famous law that Gordon Moore said that every 2 years we will have twice as many transistors within integrated circuit. And he made that projection based on how rapidly semiconductor technology was growing. But right now we met the physical limitations of that technology. We cannot pack any more transistors in a microchip because we will experience quantum effects, and all of the assumptions that we had about semiconductor technology will not hold anymore. And the same thing is for the clocking speed. Above gigahertz scale, we cannot expect the same behavior of these semiconductor devices, because at that at those speeds, we again have to consider quantum effects and some delays due to them. So the solution how to improve computational performance and how to create better, more efficient hardware is in massive parallelization rather than better semiconductor technology. And so far, heterogeneous computing is what actually appears to be the most promising path towards better and faster computational hardware. By the way, please feel free to interrupt me at any time or ask any questions at any time. If this is way too high level, we can dive into details and if it is too boring, we can switch gears. This should be very informal discussion among the friends and colleagues. This is schematics of a node on a Sierra supercomputer that was deployed at Lawrence Livermore National Lab, and I was part of that effort, working on some of the Livermore's computational libraries that we developed and deployed on this machine. And I'm not going to go into the details of this architecture and explain everything, but suffices to say these compute nodes have 2 CPUs and 4 GPUs, and each GPU has onboard memory. There are these memory blocks that are associated with these CPUs, and there is no uniform access to every piece of memory to different processing units. So you have to, when developing software for these machines, you have to think about memory space, that is where your data resides, and execution space, where your data is processed. And this makes computations more involved, and structuring the computations more involved and require a little bit more thinking. And 95% of computational power here is in these 4 GPUs. So if we want to accelerate our computations, we have to find a way how to take advantage of GPUs. And one thing about graphical processing units, or general purpose graphical processing units, how some like to call them, is that they do computations in large SIMD blocks. That means single instruction, multiple data. So, I will talk about that a little bit later. But let me just show you this, the comparison between these two. So I'm comparing one node of Summit and one node of Frontier supercomputers with a high-end workstation with i9 Intel CPU. And as you can see, that CPU has 0.2 teraflops processing power, whereas so this is the processing power of this workstation. The Summit node has 43 teraflops, and Frontier node has flopping almost 200 teraflops of processing power. If you look at the sizes of these devices, they are comparable. And the power supply required for these processing units, high-performance processing units, is about 3 times larger than power supply required for one high-end workstation, but it provides hundreds times more processing power. So if you want to see how many CPU workstations you would need to match the performance of one Summit node, the answer is about 200, and for one Frontier node, it's nearly 1,000. And why is this important? First, the space only to put all of these processing units together would be significant. And the most limiting factor is in the power supply, because one workstation takes about 600 watts of power, whereas 200 of them would take over 100 kilowatts. And this equivalent processing power for a single Frontier node, which takes about 2 kilowatts, now takes over half a megawatt. So to run these high-performance computations would require lots of power, lots of floor space, lots of maintenance. Utility bills would be significant. And with this new Exascale technology, we can bridge that gap and deliver computational power that is affordable and easy to deploy in different settings. Now, again, do I really need heterogeneous computing for power systems? What if I just do what I've been doing for years? And this is one very interesting experiment that we ran. We ran optimal power flow analysis for 70,000 bus model of Eastern interconnection. And we ran it on 2 CPUs. One is a 20-core Power 9 IBM CPU, and another one is a newer, more modern 64-core EPYC AMD CPU also. And as you can see, this is on the y-axis, I have a time to solution, and that time is broken down by different operations that took place in this computation. And what we found is that computational cost doubles on the more modern CPU. So you pay extra money, get more powerful CPU, and you get half of the performance that you got before. And why is that so? We are still actually analyzing this performance, so I will not jump to a conclusion too early. But one thing that we know for sure is that all of these CPUs are designed for parallel computations. And here we ran traditional ACOPF code, optimal power flow analysis code, that is using single-threaded algorithm, and it is not using any of the parallel capabilities of these CPUs. And it is not far-fetched to think that since our computation that we ran these CPUs was not designed for parallel computing, that it would hit some unexpected obstacles on these modern CPUs, because they are designed specifically for parallel computations. So this means that there is really no way of staying in the past and ignoring all the computational science that has been done over the past 10 years in terms of parallel computing, and especially accelerated computing. Now, another misconception that people have often is that, okay, I put my code on GPU and I get 100 times speed up. And unfortunately, this is not happening. Implementing code on GPUs requires also different mathematical algorithms, because GPUs give you fantastic acceleration. They have incredible computational power, but they require different mathematical approach to harness that computational power. And I here listed some of the issues that we deal in power systems analysis. So we have very sparse and irregular structure of the systems that we are analyzing. And that leads to some modeling challenges, how to parallelize these models to begin with. And also leads to very ill-conditioned linear problems, underlying linear problems. And we don't have good techniques for solving those problems. And these are all the problems that, these are all the challenges that we worked on at the Exascale Computing project, because we had to solve this before we were able to deploy these computations on GPUs or on heterogeneous architectures that have GPUs and CPUs. So in the remainder of my talk, I'm going to give you a flavor of what these challenges are and how they look like. And again, please feel free to interrupt me if there are any questions. And also don't expect that I will provide you all the answers and that we solved all of these problems. We just scratched the surface, and this is one huge and promising research area to continue your work in. So the way how hardware accelerators, such as GPUs, parallelize computation is that they operate on warps of 32 threads. This is what NVIDIA GPUs do, at least. AMD GPUs operate on warps, or they call them waveforms, of 64 threads. And this is how they parallelize their computations. What does that mean? This means that you have one instruction sequence control per 32 or 64 threads, depending which vendor's GPU you are using. So all of these threads have to execute the same instructions, but they can operate on different data. Now, if you have different components in your power system, so you have loads, generators, buses, lines, and each of those components does some computation. If you just naively port everything to GPU, what will happen within a single warp is that first one type of components will be evaluated, then the other type of components will be evaluated until everything is done sequentially. So you lose that parallelism because you control warps of 32 threads. You can do only one instruction sequence on all 32 of them. If you have different instruction sequence, if you have conditional branching, if you have if-then statements in there, that if-then statement will not be parallelized. You will first finish one branch and then the other branch. So what we did, we grouped different grid components within different warps. And that helped us improve our parallelism. And we first started with a proxy application that was just emulating how a power system model would operate. And based on that proxy app, we ran some tests. And we indeed got very nice speed up in the proxy app. And what I would like you to pay attention to is this graph in the top left corner here. So we are comparing here a component-wise modeling approach that we used to port everything on GPUs versus the traditional model. So traditional model, this graph is actually showing speed up over the traditional model. And as you can see, the larger the grid is, our approach is giving us a larger speed up compared to the traditional model. So we are getting up to 3 times faster computations if we avoid warp divergence that I just described on the previous slide. And if you take a look at what is happening on a CPU, this is this blue line, we are getting more or less the same performance on CPU because there is no warp divergence on CPUs. You have one instruction control sequence per each thread, so you don't need to do that. And there, as you can see, the speed up is unremarkable, as we expected it would be. So this tells us that for GPUs, we need slightly different algorithms and a slightly different setup of the computation. So what we have done in our simulation tool ExaGO, and I believe Srirang Abhyankar, who is the lead developer of this tool, has also gave his presentation here. So you might have seen this slide before, but let me just walk you very quickly through this. So in a traditional computation, you would read your data, you would set up your data structures, and you would solve the problem. In GPU computations or in heterogeneous computations, we first read the data and then we rearrange that data in a way that that we avoid warp divergence and that we maximize data coalescence on GPUs. And then we deploy these computations on a GPU. So we need to do this analysis first to redeploy data. And this, by the way, is one-time copy data from one set of data structures to another data structure. So this is a really minimal overhead that we need to do in order to harness the power, computational power of GPUs. And all of this is present in ExaGO simulation framework, which is publicly available software under permissive open source license. So all of you can use it. It is still very much a research tool and it is under heavy development. So it requires some expertise to use, but we are working on it as we speak. And I also have to say that solutions that we have in ExaGO are by no means the complete solutions and perfectly optimal solutions for execution on hardware accelerators, there is still quite a bit of work to be done, but at the same time, we are quite proud of what we have accomplished. And just last week, we have run ExaGO simulations on 9,000 nodes of frontier supercomputer, and this computation scaled on over 65,000 GPUs. So this is, first of all, this is the largest power systems analysis performed ever. And this is an example how, with a little bit of ingenuity and thinking about how to structure your computation, you really can deliver really fast and efficient computation and take advantage of new hardware that is being developed. Now, the biggest issue for these analyses is that underlying linear problems, linear systems that are created during the optimization for optimal power flow analysis are extremely ill-conditioned and sparse. So what we have seen is that solvers, linear solvers that have been traditionally used for past couple of decades, such as MA57, outperform by wide margin existing off-the-shelf linear solvers that have GPU capability. What is even more disturbing is that on these ACOPF problems, what we see is that when we run computations on GPU, we get performance degradation, not a performance improvement. And this is this was a big eye-opener for us. So these are results from some 3 years ago. And we realized that if we want to solve these problems and deliver computations that are usable for domain experts, we have to work on our own linear solvers. And first such prototype was developed in collaboration with NVIDIA using refactorization approach. And just to show you very quickly schematics, what is happening here. So this is how you would solve linear problem AX equals B. And a whole bunch of these problems is created during one analysis, whether you are talking about dynamic simulations of power grids or optimal power flow analysis where you run some optimization algorithm. So you first reorder your linear system to get some favorable structure of your matrices. Then you do symbolic factorization. Then you do numerical factorization. Once you have L and U factors, then you can do triangular solve. And eventually you might need to do iterative refinement to improve the quality of the solution. So the first 3 blocks all require conditional branching and lots of data movement, which degrades performance on GPU dramatically. So only things that we could run triangular solve and iterative refinement on GPU with some efficiency. So what we did first numeric factorization on a CPU. And then we reused factors and permutations vectors for refactorization on GPU. So on CPU, we would use KLU to obtain L and U factors with their sparsity patterns and permutations vectors. And then we would move all of that on GPU and then run only refactorization using QSolver RF or QSolver GLU solvers available from NVIDIA. In the meantime, we developed different refactorization and factorization routines, but this is what we used as the first test trial. And when you do that, then this last step, iterative refinement, becomes even more important because when you are doing static pivoting when solving linear solvers, then one after another your solution may degrade. And of course, this makes sense only if you are solving linear problems that arise in some simulation, or if they arise in some optimization algorithm where you are solving a series of linear problems with the same sparsity pattern. Then you can do that very coolly using and get a really good performance. And this is where you would use your linear solvers in most practical applications. So since then, we identified multiple promising directions. Some of them are related to NVIDIA solvers. We are working with AMD to get similar solvers implemented in ROCm library that is deployed on AMD GPUs. But as you can see, every single solution that we got so far outperforms any solution that we could get with traditional technology on CPUs. And just one word, so this is all of these computations are done for optimal power flow analysis, and I believe this is again 70,000 bus system for Eastern interconnection. This is a synthetic model from Texas A&M, and the only accelerated part, part of the computation that runs on GPUs is the linear solver. So everything that is yellow and below is running on CPU, so it's not going to be accelerated. Green bars represent numerical factorization, including the first factorization and subsequent refactorization. So this is average cost per iteration of optimization solver, or per step of the AC optimal power flow analysis. And as you can see that we get massive speedups when we are talking about factorization. And we still have to do some work on triangular solve and subsequent iterative refinement, because as you can see, Ginkgo solvers do it very efficiently, but NVIDIA solvers are not as effective in solving that. And by the way, we are just planning a meeting with NVIDIA engineers to work on this very specific issue. Now, another topic that I would like to address is how to write your code on GPUs, because if you look at GPU specific code, it looks very cryptic, it looks very uninviting, and many people say, oh my God, I don't want to touch this, and I don't want to do anything with these low-level languages such as CUDA and HIP and whatnot, and I don't want to think about thread blocks and grids and whatnot. So the good news is that computer scientists have invested quite a bit of work in developing portability libraries or abstraction layers, where you would still run your code as, or write your code as you would without any GPUs in mind, but you would be able to run that code on multiple platforms. So what does this mean? Typical C++ memory allocation includes new command. There is an Umpire abstraction layer for memory management on heterogeneous platforms. And Umpire can allocate memory for you on many different devices. All you need to do is you need to specify where you want to allocate that memory. And this here stands for unified memory. So you have an overhead of a couple of lines of code that you have to add, but you can allocate your memory wherever you want without getting into the gory details of the specific or vendor specific applications. And you can run that very same code on different GPUs, different platforms, without actually changing your code, only with specifying the hardware type when you compile your code. And same as Umpire is abstraction layer for memory management, RAJA is abstraction layer for parallel execution. So it will parallelize your for loops. So this is just a simple example of dot product. How would you implement it on CPU inside for loop? And again, for RAJA, you have to specify policies that tell you where you want to execute this. And in this case, I want to execute it on NVIDIA GPUs. So I specify CUDA-based policies, and I have to define this lambda function. But once I do that stuff, I again get some overhead in typing of a few lines of code, but whatever is inside my loop look exactly the same. So the code on the left I can run only on CPU-based hardware. Code on the right I can run on any hardware without changing the code, only specifying different execution policies. And this is a huge benefit when you deal with different hardware platforms. Of course, one thing that you have to be aware of is that your code, whether it is running on CPU or on GPU, it has to be thread safe. So there should be no interdependencies between nearby threads. But this is true of any parallel computing. Now, one great thing about abstraction layers is that you can do most of the debugging on a CPU. So the code that we ran last week on a supercomputer, I initially debugged it on my laptop, and 90% of debugging I did on my laptop, where I have CPU tools that are usually easier to use and more manageable than debugging tools for GPUs. And the reason for that is because these RAJA and Umpire abstraction layers removed all the nuances of GPU programming from me. They hid them below. So when I ran and verified that my code runs in a thread parallel fashion on a CPU, when I moved it to GPU, it just used different backends of RAJA and Umpire libraries, but everything else remained the same. So I was able to catch most of the bugs there. And then when the remaining bugs, we had to use more advanced debugging tools that are required by GPU. So this is something that enabled us to port very complex software libraries to GPU with minimal effort. And especially when we needed to switch between NVIDIA GPUs to AMD GPUs. If we, because as I mentioned at the beginning of my talk, Frontier is using AMD GPUs. At the time when we were developing this code, these GPUs were not available. They did not exist, literally did not exist. So we did all of our GPU tests on NVIDIA, and we believe that what worked for NVIDIA will work on AMD. And after that, when AMD GPUs became available, we were able to move our code there. And most of the projections that we made on one type of GPUs worked on the other type of GPUs. And it took us several hours only to transition from NVIDIA platform to AMD platform. If we used the vendor-specific languages, such as CUDA or HIP, it would probably take us a month. So this is also a huge difference in efficiency. So I just noticed that there are a couple of questions that were posted in a chat box. So let me address them right now, and we can move on with the presentation. So first question reads, how difficult is to parallelize and solve power system problems, for example, optimization, when there may be many dependencies in these problems? This is an excellent question, of course, and these dependencies are usually expressed through constraints. The short answer is it requires a little bit of effort, but it's not all that difficult. And this component-based modeling approach that we tested first on steady state prototype, steady state simulation prototype, is completely applicable to optimal power flow analysis. Each component contributes its piece to the objective function, well, actually, mostly generators, and each component contributes its piece to different constraints. In a component-oriented modeling approach, you can avoid things such as warp divergence, and you can create favorable data structures for execution on GPUs. Another question is, could you comment on data movement techniques to improve data exchange between different processing units in exascale computers? The short answer to that is that you really want to limit data movement as much as possible. When you are dealing with distributed memory architectures, you really need to figure out how to minimize the communication. Sound partitioning of your problem is something that is very important in this case, and I will address that in next slide or two. How much time do we have left? Okay.
You have 10 minutes, Dr. Slaven. Yeah.
Okay. Awesome. Just as much as I need. If we move from the single optimal power flow analysis, which we can fit on a single accelerator device, to a security constrained optimal power flow analysis, where we want to optimize our problem with respect to all contingencies and all stochastic scenarios that we can think of, we get a much bigger problem, which has this block arrow structure that we can exploit. Today, there are no linear solvers that can solve this linear system that I shown here. We can do a lot with our GPU solving techniques, but going beyond individual ACOPF to a security constrained ACOPF is a big step, and we are not there yet. But what we can do, we can make a relaxation of this problem, and instead of computing this objective function and minimizing for this objective function, we can use a two-stage optimization method, where we optimize first for contingencies and then communicate this to a master problem that collects all of these minima and optimizes the performance of the whole system. So in this particular case, these coupling variables X are resources that you cannot adjust to respond to a contingency, where variables Y are resources that can respond quickly, and you can adjust power output from them depending on what happens in terms of different contingencies or different weather scenarios. We also assume that we can run different scenarios with different wind and sun profiles. This partially answers the question how we do the data movement. So we minimize the data movement, and we use this primal decomposition MPI optimization engine that breaks this large security constrained optimal power flow analysis into two stages, and we iterate between these two stages until we converge to a global solution. But in all this communication, moving data between different devices is reduced to the minimal amount. And how does it look like in reality? We run different scenarios. We supply the data for different ACOPF sub-problems, we use this primal decomposition MPI engine to assemble the full problem on a single node. And through iterations where we parallelize most of the compute-intensive work, we get to a solution that, for example, grid operators could use. And just as a reference, we ran order of 103, I believe, contingencies and scenarios like this. So there were 103,000 of these ranks, and we ran ACOPF within less than 20 minutes. So this is quite an impressive result, and we are still optimizing this code, and we will probably be able to run this under 5 minutes. This is more like a demonstration of power, because it is unlikely that you would really need to optimize with respect to hundreds of thousands of different contingencies, but it is guaranteed that going in the future, we will have computational power that will allow power systems experts to think big and to explore different scenarios very rapidly and get more get a more reliable operation of power grid and resilient as well. So just to summarize, heterogeneous computing opens new frontier of for computing technologies and for different analyses. What we have done for the power systems analysis, we showed that actually with new computational technology, we can provide much more powerful decision support tools to power systems engineers. And we also show that when working in large teams, diverse teams, where you have people with different skills, with different perceptions and backgrounds, we can come to fantastic solutions very quickly and deliver computations that were only yesterday considered infeasible. And that, again, in turn opens different opportunities for grid operation and planning. And to be fair, even though our results look very impressive in terms of scale and performance, we just scratched on the surface. And we can optimize our code quite a bit more. We can think about more efficient mathematical methods that will take advantage of these new computational platforms. And I look forward to collaborating with you guys to find those solutions. And with this, I would thank you for your attention, and I would be happy to answer any questions that you may have.
Thank you so much, Dr. Slaven. I think you nailed it. There are a lot of challenges. I think it's so nice to see, how your portable libraries are, able to address, some of these, to accelerate the different hardware thing. Well, I have a couple of questions that I think I have made a note here. Right now, you're focusing only on power systems, ACOPF kind of problems, but are there any other use cases that that we are also looking at? I know from a perspective of bus systems, from a power grid, makes sense, and the 20 minutes that you said, and that's outstanding. Still, that you are trying to reduce that time, but how do you see this CPU GPU kind of framework that you talked about? When cloud comes into picture, is this all on the cloud, or how is your interface on these things are running on a dedicated HPC, or could you shed some light on that?
Oh, that's an excellent question, and thank you for asking. First of all, ACOPF analysis, actually stochastic security constrained ACOPF, was our challenge problem. And it was not intention to solve one singular problem, but to develop capability for solving a family of problems in there. So we can easily reuse all of this capability for electromechanical transient simulations and for electromagnetic transient simulations if we want. So most of these pieces that we have developed are reusable and not tied to specific problem. Similar to this two-stage optimization problem. It is just an approach to break a large problem into more smaller ones. People who are as old as I am remember that these two-stage computations were very popular back in the 80s when we did not have sparse linear solver technologies, and we needed to break these problems because dense problems were very expensive to solve. All of these methods are reusable and can be easily modified for different problems. Now, in terms where you want to run these test cases, I would just go back to the beginning of my presentation. So it is just one node of a supercomputer that gives you equivalent performance of a cluster of traditional workstations. So you really don't need a cloud, or you don't need a supercomputing resource to run pretty sizable computations. It is quite feasible, in my opinion, to have a workstation. And by the way, NVIDIA is already producing workstations like that. They are called DGX computers. So you can have one workstation that has several GPUs in there, and this will give you a massive performance or massive computational capability increase over whatever it's used nowadays in practice. But these workstations should be fairly easy to maintain. They don't draw too much power. They don't require massive cooling resources. So the main advantage, and I want to get that message across, main advantage of heterogeneous computing and exascale computing is that it delivers highly concentrated and portable computational power to multiple possible users. So you don't need to use a cloud. You don't need to maintain high performance computing center at your institution. You can use a relatively small and easy to maintain workstation and do really, really massive computations.
Great. So let's see. As the audience is mostly graduate students and postdocs across universities, what do you recommend in terms of the support system available on the ExaGO platform when they want to configure your software for different types of use cases? Do they have any good libraries, or there any, I'm not sure how, I have not looked into the ExaGO platform yet. I'm just trying to ask the question to see where do they go.
So that's an excellent question. I believe the best place to go is, of course, to the ExaGO website, or actually GitLab site. And I'm trying to get this link. And probably starting from ExaGO is the best place to start from. And I put this just in the chat box here. So ExaGO can run on your laptop. You don't need any supercomputing hardware. You just configure it without GPU options and learn how to use it. It can read math power files as its inputs, and it can perform computations on your laptop relatively quickly. So you can, as a starter, you can do quite a bit of work without any supercomputing resources. And whenever you have access to a GPU-based machine or something like that, you can deploy ExaGO there. Now, I have to warn everybody that ExaGO is still research software. It's not production quality software. So there is some learning curve there. And of course, some people don't make any bugs when they code. We are not those people. So our code still has quite a few bugs. And since it's been used mostly by us, we would welcome people who will try different things and use it in a different context. And if you experience any bugs, please report them. We always look for external collaborators, and we always look for user feedback.
Great. Are there any white papers also available on this GitHub on ExaGO, or are there anything that you suggest for reading for before they get started with the coding?
So I believe. So let me just.
I just want to direct people to make sure.
I believe the GitLab GitLab repository for ExaGO has a very nice documentation, and I'm sharing that with you. So I would start from there, and it has description of each of the modules here, how to use them, and what these modules do. I have to admit that we are really way behind in writing papers as opposed to the development that we have done. There are several papers on ExaGO and optimization engines and everything that we have done, but they are dated because our results are far ahead of that. So one part, as we are wrapping down our project, one of priorities for us is to document what we have done and to publish the most recent results in peer-reviewed papers.
Great. Jameson, do you see any other questions on chat window?
No, I think everything's been answered.
Okay. And then let me just ask one more question. So what is your, interactions with NVIDIA? I mean, you mentioned about vendor-specific needs to be, integrated into this platform, even though it'd be nice to have a very generalized solution where that could be customizable, for, whatever ways the vendors prefer. I'm just curious to see, because, the thread parallelism that you talked about is actually, need to be addressed by the vendors, but I'm just curious to see any thought on that.
So it should be addressed by vendors. Problems such as power systems or systems engineering problems in general have not been in vendors' focus, especially nowadays that we have this machine learning and artificial intelligence. So the customer base for AI is much bigger than customer base for power systems. So that's why we see this imbalance, that we have hardware and software support for one area and other very important areas for technology development. I wouldn't say they are left out, but they don't receive as much attention as they should. There are several solutions outside of vendor support, such as solutions by Ginkgo team that develop linear algebra primitives for different computations. But also vendors, so this is one great thing about Exascale Computing project, is because it drew attention of vendors and paid vendors to work on problems that different technology areas are interested in. So I would say it is a multi-pronged effort from us influencing vendors to deliver some of their to deliver libraries that are optimized for their hardware, but also outside of the vendor's sphere, there is also lots of people who are doing great work as researchers and national lab scientists.
Thank you so much, Dr. Slaven. I appreciate your time this morning. It's really honor to have you to have this talk, and we will make this recording available for everybody, and we'll send you the link. We'll also receive a plaque from UND and also from our dean as a token of small appreciation from us for your time and effort. And we'll continue our conversation offline, and look forward to collaborate with you on this great work, what you guys are doing.
Sounds great, and thank you for inviting me. It was my pleasure to be able to share at least some of the results of our research with you guys, and I look forward to future collaborations.
Great, thank you. This concludes the webinar.
Thank you. Bye.